Good morning. Today is Thursday, February 11th. I thought it might be helpful if I make a video with some review problems similar to some of the labs that we've done, or maybe in some cases identical to the labs. So I think what I'll do is I'll do an example problem similar to lab 3, number 1, and I'll do another example problem that's pretty similar to lab 3, problems 2 and 3. And then I think what I'll do is I will go ahead and put Lab 5 in Tinkercad. So if you had any trouble putting Lab 5 into Tinkercad, it'd be a good idea to watch this video so that you understand how to do it and it makes sense in preparation for the exam. And then the last thing I'll do in this video is I will actually give you a little bit more help on Lab 7. Lab 7 is not actually due until Sunday, whatever date that is, but I'll give you a little bit more help in as you work through Lab 7. So the first thing I think I'll do is an example problem that's pretty similar to Lab 3, number 1. So I'll switch over to the document cam. All right, here's the first circuit that I will work through as an example. I've never seen this circuit before. I just made it up before I made this video. So let's see what we get. Sometimes when you make up circuits, you get some weird, funky answers, but I don't think it'll be too funky. So I went ahead and drew this for the sake of time. So if you want to, you could pause this video and you could draw this. And actually what I'd really recommend you do is pause the video and draw this out and then work out the problem. And then after you've worked out the problem, then watch the rest of this video and you can check your work against mine. That's what I would really strongly recommend you do. So I will go ahead and assume that you have done that now. So I'm going to go ahead and start solving this problem. So what are we going to do? Well, the first step in circuit analysis problems that I told you to follow in this procedure that we have for circuit analysis problems. The first step is to look at this circuit and say, can I combine all of these resistors together into an R total? Because if so, that's probably the most intuitive way to do it. It may or may not be the fastest, but it's probably the most intuitive way. And in this case, can we? Well, we can definitely combine these two, and then we can combine these two with that in parallel, and then we can combine all of this with this in series, and then we combine all of this with this in parallel, and there we have it. We have an R total. So let's do it that way. I think I'm going to do it that way. So I will make some dotted lines around here to indicate what I'm going to combine and when. So let's combine these first and call that R equivalent 1. That's the first thing I'll do. And then after I combine those two, obviously in series, then I will combine these three, R3, R4, and R5. These are in parallel. So I will combine these all together into R equivalent 2. That's what I'll call that. And then after I have that, then I can combine this with this in series. So I need a different color. So we will combine all of these together, and I will call that R equivalent 3. All right, and then the very last step, I don't think I need to draw this in because the last step is going to be R total. That's kind of obvious. So the last step will be combining R3 with R1 in parallel because the current can either go through R1 or it can go through all of this mess over here. So let's do that, and I will redraw the circuit at each step. So let's get to it. I'll do all my work in green, just so you can see the blue is what was given, that was the problem, and the green is the work that I'm going to do in solving it. So first, we gotta work our way from the farthest point away from the voltage source back to the voltage source and getting R total. So the first thing I'm gonna do is combining R4 and R5, and that combination is R equivalent 1. So R equivalent 1 equals R4 plus R5. R4 is 40 ohms. R5 is 50 ohms. So I can do that in my head. R equivalent 1 is 90 ohms. So far, so good. And I think I will redraw the circuit at each step, like I said. So here's 48 volts, and then we've got R1, and then we've got R2, and we've got R3, and now we don't have R4 and R5, we just have R equivalent 1. Right, so that is our simplified circuit. Now, we have replaced that circuit with a slightly simpler circuit, which is that. Now, I'm going to combine R equivalent 1 and R3 into R equivalent 2, like I had up here in red. But I'll just keep with the green. So 1 over R equivalent 2 equals 1 over R3 plus 1 over R equivalent 1. And R3 is 30 ohms, so I can plug in that number. And R equivalent 1 is 90 ohms, so I can plug in that number. So 1 over R equivalent 2 equals 1 over 30 ohms plus 1 over 90 ohms. This I'm going to need my calculator for. So I'm going to take parentheses 1 divided by 30, close parentheses, plus parentheses 1 divided by 90, close parentheses. That's my answer for that. And then I take the inverse of both sides. So I take 1 divided by that. And I get R equivalent 2 is equal to 22.5 ohms. 22.5 ohms. Very good. All right, I'm well on my way. So now I'm going to redraw the circuit that is simplified by combining these two. So now my circuit looks like this. Here's R1, here's R2. And now I've combined R3 and R equivalent 1 into a single resistor, which I call R equivalent 2. Okay, so it's looking a lot simpler. But now I see that these two are in series. Any current that goes through here must go through here. And I am going to call that, if you look back, we're combining R2 with R equivalent 2, and we're going to call that R equivalent 3. So R equivalent 3 equals R2 plus R equivalent 2. R2 was 20 ohms, and R equivalent 2 was 22.5 ohms. So R equivalent 3, I'll write on new line, R equivalent 3 equals 42.5 ohms. And now I can redraw the circuit again, even simpler. R1, and now I'm combining R2 and R equivalent 2 into R equivalent 3. And that is going to be our total. All right, so my last step is to find R total, and these are in parallel. So I have 1 divided by R total equals 1 divided by R1 plus 1 divided by R equivalent 3. Plug in numbers here. R1 was 10 ohms. And R equivalent 3 is 42.5 ohms. So once again, I need my calculator for this. I take parentheses 1 divided by 10, close parentheses, plus parentheses 1 divided by 42.5, close parentheses. Enter, and then I take the inverse of both sides. So I take 1 divided by that answer, and I get I call that 8.1 ohms. All right. Our total equals 8.1 ohms. All right, so our total equals 8.1 ohms. So it doesn't actually ask for this in the problem. So we don't necessarily have to fill our total in there. It also doesn't ask for I total. We could find it. Let's go ahead and find it just in case is useful for us at some point. So we know V total equals I total R total, and I total, no, we were trying to find I total, all right? So we were going to rearrange this. So we know V total and we know R total. We're going to try and find I total. So I total equals V total divided by R total. And V total is given as 48 volts. And R total is 8.1 ohms. So now we can find I total. It may or may not be useful for us, but we can find it. 48 divided by 8.1 gives us 5.93 amps. So that is I total. So that's wonderful, but what I really want to find is all these component current values and all the component voltage drops, and then eventually the voltage at these nodes. So what I'm going to do is start working back up towards the original problem and figure out what I can solve at each step, working my way back up. All right, so now we're going to start. Well, we already started with the simplest possible circuit by finding I total and V total and R total. And now we can go to this circuit. So maybe what I'll do is on the way back up, now I'm going to switch colors to purple. And I'm going to think about what I can figure out at each step as I'm going back to the original circuit. All right, so what can I do? I've already found I total, V total, R total. So now let's take a look at this circuit. What can we figure out based on what we already know with this circuit here? Well, we have 48 volts applied, and we have R1 and R equivalent 3 in parallel, right? What do we know about parallel circuits? They have the same voltage drop across them. They have to. So what I know about this is I know what V1 is. V1 is equal to a V applied here. So V1 is 48 volts. All right, great. And if I know V1 and I know R1, because all the resistance values were given, then I can find I1. I1 equals V1 divided by R1. V1 is 48 volts, and R1 was 10 ohms. So that I can do in my head. 48 divided by 10, move the decimal place over one spot, and we get 4.8 volts. So those are things that I can use. I can put those back in my original problem. So V1 is 48 volts. And I1 is 4.8. That shouldn't be volts. That should be amps. Okay, 4.8 amps. All right. What else do we know about this? Well, we know what V equivalent 3 is. That might not seem useful, but actually it probably is going to be useful. So we know that V equivalent 3 also is 48 volts. All right, so that might not seem useful, but if we know the value of R equivalent 3, and we know the value of voltage drop across R equivalent 3, then we can find the current through resistor equivalent 3, and that might actually be useful. So I need some room, so I'm going to come down here. I equivalent 3, the current through this resistor right here, even though it's a fictional resistor that we made up, we can still use it. It could still be useful. So I equivalent 3 equals V equivalent 3, which is 48 volts, divided by R equivalent 3, and R equivalent 3 is 42.5 ohms. And now I'm going to plug that into my calculator. 48 divided by 42.5 tells me that I equivalent 3 is 1.13 amps. All right, that might not seem useful. I mean, you can't write that in here. It doesn't apply to any individual component. But check this out. R equivalent 3 is nothing more than R2 and R equivalent 2 in series. So really, this is just representing these two in series. And we know the current through here, And what do we know about components in series? We know that if they're in series, they must have the same current through them. So the current through here must be the same as the current through here and the current through here, because these are just replaced with R equivalent 3. So if I know the current through here, then I automatically know what I2 is, and I know what I equivalent to is. So I2, I can just write it down without any calculation because it's part of this resistor right here. And they're in series, so I know the current. So I2 equals 1.13 amps. And if I know I2, I also know R2, so I can find V2. V2 equals I2R2 from Ohm's law. I2 is 1.13 amps, and R2 was 20 ohms. So I could probably do that in my head, but I'm going to do it in the calculator just to make sure. 1.13 times 20 gives me 22.6. 22.6 volts. So these two are useful. I can write those in. I2 equals 1.13 amps, and V2 is 22.6 volts. V2 is 22.6 volts. Good. Now, I might also want to know something about R equivalent to. I already know I equivalent to. It's the same as I2. So I'll write that down. I equivalent to equals the same, 1.13 amps, because they're in series. And then V equivalent to, I'm going to come down here again, V equivalent to equals I equivalent to times R equivalent to. I know both of those. So that's 1.13 amps times, what was R equivalent to? I got to go back here, 22.5 ohms. 22.5 ohms. So V equivalent to is 1.13 times 22.5 gives me 25.43 volts. 25.43 volts. Good. So now I know everything there is to know about this resistor and this resistor. Now I can come back to this circuit, and I know everything there was to know about that one and that one. And now I'm going to say, you know what, R equivalent 2 is really just R3 and R equivalent 1 in parallel. And what do we know about parallel resistances? Well, they have the same voltage drop. So whatever the voltage drop of R equivalent 2 was, that's going to be the same voltage drop as V3 and V equivalent 1. It has to be because these are in parallel, and they just represent R equivalent 2. So these must have the same voltage drop as R equivalent 2. So I can write down what V3 is and what V equivalent 1 is. So let's do resistor 3 first. So V3 just has the same voltage drop as R equivalent 2, which was 25.43 volts. 25.43 volts. And of course, if I know V3, and I know the value of R3, I can find what I3 is. So I3 equals V3 divided by R3. V3 was 25.43 volts, and R3 is 30 ohms. So I3 equals 25.43 divided by 30, which gives me 0.85 amps. Those are both useful. I can write down V3 and I3. V3 is 25.43 volts, and I3 is 0.85 amps. 0.85 amps. Good. Okay, and then just like before, I know what V equivalent 1 is. I can just write it down. V equivalent 1 is the same as V3 because they're in parallel. So V equivalent 1 is 25.43 volts. So I equivalent 1 is equal to V equivalent 1 divided by R equivalent 1. V equivalent 1 is 25.43 volts, and R equivalent 1 was 90 ohms. So what is I equivalent 1? 25.43 divided by 90 gives me 0.28 amps. All right, so that's going to be useful for me. So I know what V equivalent 1 and I equivalent 1 are now. And R equivalent 1 was really just R4 and R5 in series. What do we know about components in series? They must have the same current. So R4 and R5 are in series, and combined they represent R equivalent 1. And so whatever the current going through here is also the current going through R4 and through R5. So I immediately know that I4 and I5 are equal to I equivalent 1, which was 0.28 amps. So I can write both of those in here. And now I just need to calculate these voltage drops. V4 equals I4, which was 0.28 amps, times R4, which was 40 ohms. 0.28 times 40 gives me 11.2 volts. V4 is 11.2 volts. And similarly, V5 equals I5 R5. I5 was 0.28 amps also, and R5 was 50 ohms. So 0.28 times 50 gives me 14 volts. All right. The last thing here is to calculate the voltage at these nodes, node A, B, C, and D. So the easiest thing to do is to start from ground. There's a symbol for ground. So that's at 0 volts. So we're basically told that the voltage at D is 0 volts. So write that in. And then the easiest way to get from ground to point A, all right, well, the easiest way is to go through this voltage supply. So this is all at 0 volts because it's all connected with no load in between it. This is all at 0 volts, and from here to here, I gain 48 volts. So the voltage at node A up here must be 48 volts. By the way, another way to look at that, what was the voltage drop across resistor 1? It was 48 volts. So another way to look at that was, I dropped 48 volts from here to here, and I know I'm at 0 volts here, so what must the voltage be here? Well, it must have been 48 volts. So there's multiple ways you can do these types of problems. All right, and to get the voltage at node B, okay, we are at 48 volts at node A, and then how much voltage do we drop from here across resistor 2 to get to node B? Well, what's V2? V2 is 22.6. So we're at 48 volts here. We drop 22.6 volts from here to here. So what are we at here? Well, whatever 48 minus 22.6 is. 48 minus 22.6 gives us 25.4 volts at node B. And then finally, we want to get the voltage at node C. So there's two ways of doing this. We could say, hey, we're at 25.4 volts here, and then we drop whatever V4 is from here to here. So what was that? So 25.4 minus V4, V4 is 11.2. So what is 25.4? 25.4 minus 11.2. Were those the right numbers? Yes. So that tells me that voltage at node C is 14.2 volts. So I'll write that down, and then we can check that. There may be a little bit of rounding error, but we can check that by saying, all right, the easier way to do that really would have been to say, all right, I know what V5 is. V5 is 14 volts. So from here to here, across resistor 5, I drop 14 volts. So if it's 0 volts here at ground, and I dropped 14 volts from here to here, then the voltage here must be 14 volts. So we said 14.2. There's a little bit of rounding error in there, but hey, what's 2/10 of a volt among friends, right? There was definitely some rounding in there. We rounded to the, say, the hundredths of an amp and things like that. So if you're within 2/10 of a volt on the exam, you're definitely going to get the problem right. That's easily within 5%. And if you're within 5 or 10% of the correct answer on the exam, it's going to be counted right. I will make sure that it's set that way. The second problem I will do right now as a review is a problem that's kind of similar to number 2 and number 3 in lab 3. So here's a circuit where we've got two voltage supplies. And the first question we should ask ourselves is, can we simplify this into an R total? Can we combine these into an R total? The answer is not really. There's not really anything that I can see that you can really combine here. Yeah, I can't combine anything. So that's not going to work. So we're probably going to have to use KVL and or KCL. So if we know we're going to have to use KVL or KCL, the next step is to draw our assumed current directions in. And we're given that the current through R1 is flowing left to right with 2 amps. And the current through resistor 3 is 1 amp, also flowing left to right. So it doesn't matter, I might be wrong here, but I'm going to assume that the current is flowing down through resistor 2, and I will also assume it's flowing down through resistor 4, and I will assume it's flowing up through resistor 5. I think those are pretty good guesses, but honestly, I don't know. I have not worked this problem before. And we'll see what we come up with. All right, so we've got everything labeled, right? And we've got our assumed current directions. So now what we're trying to find is nodes or loops where there's exactly one unknown. But you know what? I can do a little bit before that, because here and here I know the current and I know the resistance. So I can actually do a little bit before looking for nodes or loops. So we can solve for V1. V1 is equal to I1 R1, so that's 2 amps times 10 ohms, which gives me 20 volts. So I can write down V1, it's 20 volts. And I can also write down I1, it was actually given, so it's 2 amps. And same thing for resistor 3. V3 equals I3, which is 1 amp, times R3, which is 5 ohms. So V3 equals 5 volts. V3 equals 5 volts, and I3 was given as 1 amp. All right, so it's always worth keeping in your head what resistors do you know about and what don't you know about, or what components don't you know about. So I know everything there is to know about that one. I know its resistance, its current, and its voltage drop, and also that one. But I don't know VL, I don't know that one, I don't know that one, or that one, or that one. So we got a little bit of work ahead of us. So what can we do? What's the next thing that we can do? Well, we need to look for loops with one unknown voltage drop, or nodes where there's one unknown current flowing into or out of that node. All right, so try to find a loop where there's only one unknown. Does this loop work? No, because I don't know that or that. Does this loop work? No, because I don't know that or that. Does this loop work? No, because I don't know anything in here. I don't know any of these. So I don't see a loop. There's no loop that I can see. I could be missing something, but there's no loop that I can see where I can find just one unknown voltage drop. So I'm going to switch. I'm going to look for nodes where there's one unknown current flow coming into or out of that node. So look for a node where there's one unknown current flow. And there is one that jumps out at me right here at B, because I know that current coming in, I know that current coming out. So I can find the current through I2. So I'm going to do KCL. I'll do it in this column over here. I'll start a new column. KCL at node B. KCL says add up all the currents coming in on one side, set it equal to all the currents coming out on the other side. What's coming in? I1. What's coming out? I2 and I3. So our equation looks like I1 equals I2 plus I3. We know I1 and I3, so we need to get I2 by itself. So subtract I3 from both sides, and you get I2 equals I1 minus I3. Now plug in numbers. I1 is 2 amps. I3 is 1 amp. So I2 is 2 amps minus 1 amp, which is 1 amp. So now I know I2 and I know R2, so I can get V2. V2 equals I2 R2. I2 is 1 amp. R2 is 20 ohms. So that's 20 volts. So I can write that in. I2 equals 1 amp. V2 equals 20 volts. All right, very good. So now I know everything there is to know about that one and that one and that one. So what should we do next? Well, there are probably several different things that we could do next. Yeah, I can see at least 2 different things that we could do next. But I think the next thing I'm going to do is a loop on the left side. So I'm going to do a KVL loop, left loop, and I'm going to go clockwise because these arrows are going that direction. So clockwise, and I'm going to start at A. So I go from A, I go with this arrow, so it's V1, with this arrow, so it's V2, V1 plus V2, and then I come to the negative sign first, so it's minus VL equals 0. V1 plus V2 minus VL equals 0. VL is the only thing I don't know, so pull it over to the other side by itself by adding VL to both sides. VL equals V1 plus V2. V1 is 20 volts. V2 is 20 volts. So VL is 40 volts. Okay, so I'll write that down. VL equals 40 volts. Okay, so now I know everything about that component and that one and that one and that one. So we're probably halfway done or something like that. So what can I do next? Well, I can only see one other thing to do right now that jumps out at me, and that is to do a loop in the middle. All right, so I'll do that. I think I have room right here. This will be a KVL loop. It'll be the middle loop, and I'm going to go clockwise. So I will start from B. So I'm going with the arrow, and then against the arrow. So it's going to be positive V3 plus V4 minus V2 equals 0. V3 plus V4 minus V2 equals 0. Our unknown here is V4, so I want that on its own. So I'm going to subtract V3 and add V2 to both sides. So V4 equals V2 minus V3. V2 was 20 volts. V3 is 5 volts. So 20 minus 5 is 15 volts. And if I know V4 and I know R4, I can find I4. I4 equals V4 divided by R4. V4 was 15 volts. R4 was 7.5 ohms. 15 divided by 7.5 is 2 amps. So let's write those in. I4 is 2 amps. V4 is 15 volts. Now I need a new page. Okay, so what do I have left here? So I know everything about that, and that. So now, this is a lot like one of the labs questions in Lab 3, one of the questions in Lab 3, because try as I might, there's no way I'm going to be able to write a loop with isolating one of these. It's not going to work because they're together like this. So that loop doesn't work, 2 unknowns. This loop doesn't work, 2 unknowns. This loop doesn't work, 2 unknowns. So KVL is not going to work. What else could I do? Well, look at node C. I know the current coming in here. I know I4 coming out here. So I can figure out what the current is right here. It's the same as the current through resistor 5, right? So I can write a KCL equation at node C. KCL at node C. All the currents coming in equals all the currents coming out. What's coming in? I3 and I5. What's coming out? I4. And what we're trying to find is I5. That's our unknown. So subtract I3 from both sides. I5 equals I4 minus I3. I4 is 2 amps. I3 is 1 amp. So I5 equals 2 amps minus 1 amp is 1 amp. And I know R5, I know I5, so I can get V5 equals I5 times R5. It was 5 ohms, and that gives me 5 volts. So I5 is 1 amp, V5 is 5 volts, and the only component left is V sub R. So now there's a bunch of different loops I could use. I could use this one, or I could use this one, or I could use the full outer perimeter. I'm going to try to keep it easy. I'm going to use the right loop. So KVL for the right loop. And I'm going to go counterclockwise just to go with the arrows, even though either way would work. So maybe I'll start at C. So I'm going with the arrow here, so it's going to be V4, and then I come to my minus sign, so it's going to be minus V sub R. And then I'm going with the arrow, so it'll be plus V5 equals 0. So I've got V4 minus VR plus V5 equals 0. I'm trying to find VR, so move that to the other side. VR equals V4 plus V5. V4 is 15 volts. V5 is 5 volts. So VR equals 20 volts. All right. That's all the components. So now all I got left is the nodes. So we're given this ground symbol right here. That means ground. That's at 0 volts. So once again, the voltage at D is 0 volts. And then what's the easiest way to get up to node A? Probably just through here, through V sub L. So I'm going to gain whatever V sub L is. So VL is 40 volts. So I'm going to gain from 0, I gain 40, so I get to 40 volts at node A. And next is B. So I'm at, well, what's the easiest here? I'm at 0 volts here, and then from here to here, I drop whatever V2 is. So what's V2? V2 is 20 volts. So if I drop 20 volts from here to here, and here I'm at 0, I must have been at 20 up here. So voltage at B is 20 volts. Notice we could have done that another way. We could have said we're at 40 volts here, we drop V1, which is 20 volts. So 40 minus 20 also gives me 20 volts. And the last one here is voltage at node C. So the easiest way is probably across resistor 4. So from here to here, I drop V4, which was 15 volts. So from here to here, I drop 15 volts, and here I'm at 0 volts, so I must have been at 15 volts here. So this is 15 volts. And once again, there's another way. There's always another way to do it. I could say I'm at 20 volts here, and then I drop from here to here, I drop V3, which was 5 volts. 20 volts minus 5 volts gives me 15 volts. So it's good to double check your work and check it multiple ways to make sure you got the right answer. All right, so that wraps up that sample KVL KCL problem. The next thing I thought I would do, just because I think it might be helpful for you, is I will go ahead and do lab 6. Lab 6 is the latching relay, and I'll do that in Tinkercad because I know there were at least a couple people that were struggling a little bit with it. So let's take a look at it. So I'll share my screen. Here is Tinkercad, and I've already taken out the components that I'm going to use. And I've changed the voltage of the power supply to 12 volts, so it's ready to go. And I've got a slide switch that I'm going to use in place of that stop push button. And I've got the start push button. I've got a relay, and I've got a light bulb. So the first thing I'm going to do is put these on the breadboard. I'll put this on like this, and then I'll put my start push button on here, maybe about right there. And I'll put my slide switch, which takes the place of a stop push button, about right there. And I'll put my light bulb, it doesn't really matter, right there, looks good. So I'm going to start wiring things up. So I like the idea of keeping each rung in a different color. So I will, first I'll put the power supply rails here. So let's go ahead and do this first. So that's going to be my positive side. So I'll put that in red. And then the negative side is going to be in black. All right, so now I got that taken care of. Now I'll start working on my rungs. So I'll put the first rung maybe in green because that's the default color when I string a wire in Tinkercad. So I'm going to work on the first rung here. Look at the first wire on the first rung in lab 6. It goes from 12 volts to the input or the common of the stop push button, which is the slide switch here. So the common here is right here. So we'll go from right there to 12 volts. So that's our voltage. There's the first wire. That's the upper left wire in the first rung in lab 6. I move to the right on that rung, and I see that I need a wire from the output of the stop slide switch to the input of the start push button. So the output is going to be right here. So I need a wire from right here to the start push button. That's right there. There's our second wire. But look, right below that, there is another wire. It needs to go from the output of the stop push button. So one of these connections right here. And it needs to go to the common, that's the input, of CR1A1. So that's a normally open contact, but we got to use the common. That's the input for the contact. So we got to go from here, and we got to go to the common. What's the common in this relay? Well, if you look on page, I think it's 41, you'll see that the common for all the normally closed and normally open contacts on this side of the relay is this one in the middle, terminal 13. So I need to connect to one of these right here. So I'll go right there. That looks good. All right, so the next wire, I'm looking at my first rung still. I need to go from the output of the start push button to the coil. So I need to go from here, that's the output of the start push button, to the coil. The coil input is terminal 16. So I'm going to go to right there, and then I'll make this, no. And then I'll make this look a little bit prettier. I don't know. I just like horizontal and vertical lines as much as possible. And the other way that I also can energize that coil, if you look at the top rung of lab 6, I also should have a wire that goes from the normally open contact. So if you look in here, you zoom in, you'll see it's the lower left contact. It's the one over here. It's the lower left one that is the normally open. You can also see that on page 41. So I need to go from one of these connections here also to the coil. So there's actually two ways of energizing the coil, and you can see that in the top rung on lab 6. It can come from the start push button, like right here, or it can come from the normally open contact, which is right here. Okay, so that is both of the wires to energize the coil. the last wire on the first rung goes from the coil output to ground. So I'm going to come outside, I'll come over here, and then I'm going to go to ground and make it a little bit prettier. Okay, that's it. That is the first rung of lab 6. The second rung is easier. We go from 12 volts, we go from 12 volts to the common of a normally open contact, and this says CR1A2, so it's the second normally open contact, whereas the one on the first rung was CR1A1. So we already set this as the first normally open contact, so the second normally open contact must be this one. And if you need help identifying these contacts, look at page 41 in your lab manual. That's going to be the normally open contact that I got to use, but I got to connect to the common of that contact, and that is the middle one right here, terminal 4. So I got to go from 12 volts to this connection, terminal 4 right there. So I'll do this in a different color. Maybe I'll make this, I don't know, orange or something. Sure, orange. All right, the second rung is going to be orange. Now the second wire of the second rung goes from the normally open contact associated with that common. So I got to go from any of these connections to the output, the light bulb. So I'll go from right here, and then I'll go over here, and then down there. Okay, and I got to make it orange because it's part of the second rung. And then the very last one, oh, that's easy. It's just the output of the light bulb to ground. So I'm going to come down here, and I'm going to be going to anywhere in the ground rail. All right. Oh, got to make it orange. All right. Now here's the moment of truth. If I did this correctly, then I'm going to start the simulation. And now what should happen? Well, I should have to switch this slide switch to on. And then after I do that, I can press the push button and it will turn on the light, and then the light will stay on even after I'm no longer clicking on the push button. Notice the push button does not turn the light on. I'm clicking on it right now. It doesn't turn it on because the slide switch is in the wrong position. So this is like the stop push button is pressed. So to turn the light on, I got to turn the switch to the other position. And now if I press the push button just once, the light should turn on and stay on. There we go. Perfect. All right. Isn't that rewarding? I think it's rewarding. It's pretty satisfying to wire this all up correctly so it does exactly what you want it to do. So now it doesn't matter if I press the push button. Doesn't matter. It stays on. The only way to turn it off is to, well, I guess break one of these wires or to turn the slide switch off. There we go. So that's like pressing the stop push button. So now once again, it doesn't matter if I press the start push button. Doesn't do anything until I move the slide switch and then I press the push button. Now it turns on and stays on until I break the circuit or I break the latch. I break the latch. And the way I do that is by moving the slide switch. I said I would give you a little bit of help on Lab 7 as well. Remember in class on Monday, we pretty much did all of the AND logic gate. We completed the truth table, we drew out the lateral electrical diagram, we drew out the wiring diagram that looked like this. Remember this? We talked through this in class on Monday, so you can use that, it's fine, in your own lab manual. And what I think I'll do right now, I'm not going to go through all of that, but I will talk through the OR logic. So that is on page 53. That's the third one of Lab 7. So I'm not going to talk through the truth table again because we did that on Monday. So you have page 49, and we talked through the truth table for an OR logic gate. So you have that already. And if you look at page 49, you have the lateral electrical diagram as well. You have that. So you can pretty much just copy that from page 49 onto the middle of page 53 for the lateral electrical diagram. I'm going to leave the wiring diagram to you, so you can use this as a kind of as a model for the AND logic. I'm going to let you do that, but then I will show you how to do it in Tinkercad. So I will do the OR logic in Tinkercad, and you can follow along if that is helpful for you. So I will switch over to share my screen from Tinkercad. So I'm going to look at page 49 as I'm doing this because I'm fairly comfortable looking at the ladder electrical diagram and transitioning from there to the wiring diagram directly in Tinkercad. But I do want you to not skip a step, and I want you to draw out the wiring diagram in your lab manual, kind of like what we did in class on Monday. But I'm just going to use the diagram on page 49. So this is the top right ladder electrical diagram on page 49, and I'm going to put it into Tinkercad. So we know that we're going to need 2 relays, 1, 2. We're going to need 2, it shows push buttons, but we're going to use slide switches because I can't press on 2 buttons at the same time with my mouse. So we're going to use slide switches instead. And of course we need a power supply and we need an output, which we'll use a light bulb for. So I'm going to put these into my breadboard. Doesn't really matter exactly where you put them. Just kind of space them out a little bit so that you've got room to work with. And so that looks pretty good to me. So I'm going to do it line by line, and I'll use a different color for each rung. So the first rung I'll do in green, just because that's the default wire color in Tinkercad. And that top rung, the leftmost wire, goes from the voltage supply, which in our case is 12 volts. 12 volts to the input or common of our switch, which we're using the slide switch for. So we got to go from 12 volts, our power supply, to the common right there. That's our first wire. Our second wire in the middle of the first rung goes from the output of that switch. By the way, I'm calling this switch A and this relay 1, and this is going to be my switch B, and this is relay 2. All right. So I need to go from the output of switch A to the coil of CR1. That's what that first rung tells us. From the output to the coil, and the coil is terminal 16. That's what page 41 tells us. And you can also zoom in here and you can see, oh, there's the coil on the left here. Or excuse me, on the right here. Okay, so we need to go over to there. And the last wire in the top rung goes from the output of the coil here to ground. So I need to go to ground, and then I want to make it look a little better. There. Okay, I like that. That is the first rung. Got that done. The next rung, we're going to do something very similar, but with switch B and relay 2. So the first wire in the second rung goes from the power supply rail to the input of switch B. So I'm going to go from here up to here. And then the second wire goes from the output of the switch to the coil of the relay. So that's any of these points right here. And the last wire on the second rung goes from the output of the coil to ground. And I want to use a different color for all of these wires on the second rung, just for clarity. So we'll use orange for the second rung. Okay, that completes the first and second rungs of my OR logic gate circuit. And now I got the third rung, which is the most complicated one. So I need to go, let's look at the upper part of the third rung. So I need to go from the power supply to the common of CR1A. It doesn't tell us whether it's CR1A1 or CR1A2, so I can use either side of the relay. I'm going to use the lower side just because it's easier, seems like, and closer. So I need to go from 12 volts, the power supply, to the common, that's the input, the common of CR1A. So the common is this terminal 13 right here in the middle. So I need to go from the power supply rail to the common right there. All right, so I got that done. And then I need to use CR1A, so I need to use the normally open contact associated with terminal 13, which is this terminal over here, terminal 9. And I need to go from there, I need to go over to the light bulb. All right, so I'm going to get up there. All right, so I'm going to go kind of around, and then I'll go like this, and then down. All right, and now I'll make it look a little better. No. Okay, that looks pretty good, but I need to use some different colors here. So the third rung, I will make, how about blue? Yeah, that looks good. There we go. All right, so that's almost half of it. So I've got from the power supply to the common of the contact, and then using the normally open contact and going to the input of the light bulb. And then the same thing over there for the relay number 2. I got to go from the power supply to the common of the contact. So I got to go from the power supply to the common, and that needs to be blue because in the third rung. And then I need to go from the normally open contact associated with that common. So that's over here on terminal 9. And I need to go from there also to the input of the light bulb. These are in parallel. So once again, I'll make it look better in a second, but it's going to come over here. Okay, I'll make it look better now. All right. Okay, that looks pretty good. There we go. All right, we're almost done, but don't forget that very last wire. We got to go from the output of the light bulb to ground. And that will also be in blue. All right, so now if I didn't miss anything, which is always a possibility, you never really know until you test it out, but if I didn't miss anything, then our light bulb should light up anytime either one of these slide switches is in the right position. Either or both are in the right position. So let's go ahead and try it out. I'm always a little bit nervous at this point. Is it going to work? I don't know. So whenever I switch either one of these slide switches, the light bulb should turn on. Ready? All right, that works. Okay, let's turn that one off. Let's try the other one. All right, that works too. And if both of them are on, it still works. So whenever they're both off, the light bulb's off. Whenever either one of them is on, the light bulb turns on. And of course, if both of them are on, the light bulb stays on. All right. Pretty cool, I think. I think it's pretty cool. All right, so I hope that was useful. That was a review of a lot of the stuff that we have done in the past couple of weeks. We did a review of a circuit analysis problem that you don't have to use KVL, KCL with. We did a review of a circuit analysis problem that you do use KVL, KCL with. We did a review of a latching circuit like Lab 6. And we just did a review of another type of logic circuit. So now I've done the AND logic and the OR logic, almost all of those for you. So now you have to do the rest of what I didn't do just now for the OR logic. And then you have to do the same thing for the NAND and the NOR logic. Let me know if you have any questions. I'll be happy to help. Otherwise, good luck and have a good weekend.